All right, couple things here about Moodle before I go on to the PowerPoint again is that so the video links I posted yesterday in the announcements. This was from Monday's lecture. Today's lecture will be the video link will be posted in the announcements again until I could get the videos in the format like I wanted to be. And now for this upcoming exam and for the upcoming videos. So you've got Lewis structure and geometry videos here. So watch these two videos. All right, read this document here. I'm just going to pull it up in here. So this is a handwritten document. I don't have any annotation to it or nothing. Just read through it. So that way it just explains how we work with polyatomic ions. And then as you get through that, we get down to the section 9. And section 9 deals with the final chapters, basically the end of chapter 10 and 11. So in here you have a Vesper sheet. You'll want to print that off. This is just practice problems here. This is a peyote answer key. Now it says last set of videos. So you're going to watch these. So there's 4 videos here, and then there's one more PDF file which is below right here. So this is the final set of videos here, okay? And bond energy goes with the enthalpy part that I was talking to you about. So you're definitely going to want to watch this video. In fact, we'll get to bond energy before you get to it on Moodle. So bond energy really should be right up in this area here. But that's the rest of the videos. So all the videos are posted online for the rest of the semester. So make sure you definitely watch everything and take careful notes on everything, and then obviously being a part of the lecture here as we go through the rest of the weeks in the semester. All right, so last time we stopped with ionization energy, so I'm going to go ahead and pull this back up. If you need to write this down, go ahead and jot this down. And I'll give you a minute to do that if you need to. Okay, so ionization energy is the amount of energy it takes to remove an electron from an atom. And so remember, there are different types of electrons. There are core electrons, and then there are valence electrons. We did discuss this pretty in depth the other day, but just a review here, you've got your nucleus, you've got your core electrons, and then you've got your outer electrons. So all the core electrons are found in the inner shells, and then your valence electrons are found on the outside. So when we talk about ionization energy, it's how much energy it takes to remove the electron from an atom. And so the valence electrons are obviously going to be the easiest electrons to remove. And then you dive into the core electrons. Core electrons are held much tighter to the nucleus because they're closer. Plus, the nucleus has that very large positive charge, so it holds them together by the electrostatic attraction. So when we talk about the differences in the atoms, it's the position on the periodic table that makes the biggest deal here. All right, so just looking at the periodic table here, so you have your basic outline of the periodic table here. As you go from left to right, the valence electrons increases. So 1, 2, all the way to 8 over here. So the higher the number of valence electrons, the smaller the atom becomes. Remember we talked about the other day the size of the atom. So as you go from left to right, the size decreases. Now as it decreases, so when we talk about the sizes, okay, so think about the nucleus here. So the nucleus is small, and as you go left to right, the size gets smaller and smaller. Now, as the nucleus is going to be, the electrons are closer to the nucleus, is going to be held tighter. So the electrons that are found in the valence electrons here on the left side should be a whole lot easier to remove than the electrons found here in the smaller atoms. So that's a trend that we're going to be paying attention to. And so as you go left to right, as the atom becomes smaller, the ionization energy increases. So the rule of thumb to remember here is the smaller the atom, the higher the ionization energy. Now, we don't include the noble gases because noble gases don't react and they're not going to lose their electrons. So the elements that we're talking about are like 1 through 7. Now, as we talk, so first ionization energy is how much energy it takes to remove the first electron. Then you have the second ionization energy that removes the second electron, then the third, then the fourth, then the fifth, and this could go on and on and on. Now, here's the problem with it though. As you look at the individual elements, each element has their own number of electrons, their own number of valence, and their own number of core. So valence electrons are always going to be much easier to remove than the core electrons because the core is found closer to the nucleus, held tighter, as we talked about earlier. So as we look at this table here, this table is only looking at one specific row. I think this is period 3 that starts with sodium and ends with argon. Okay, so when you look at your periodic table, now this pattern shows up pretty consistently in each of the periods, but this is the one that we have in PowerPoint. Anyhow, so it requires more energy to remove each successive electron. So the first electron is easy to remove. Then you get to the second one, a little bit more difficult. Then you get to the third one, a little bit more difficult. Now, if you look at sodium, for example, here. So if you find sodium, well, the first one is 495 kilojoules per mole. So the units are kilojoules per mole. But that really is not going to make a difference here. But what we want to look at is the fact that sodium has one valence electron because it's in group 1. So sodium only has one valence electron. So when you take that one electron away, now you're diving into the next set of electrons, which are your core electrons. If you look, there's a gap here. And there's a big gap. It goes from 495 to 4,562. So this gap is because you go from a valence electron to a core electron. And as you do that transition, it takes an extremely large amount of energy to remove the core electrons because they're comfortable, they're stable. If something's stable, it's going to be much more challenging to remove it than something like a valence electron. Now, we look at magnesium. So magnesium is the second element here. All right, so we start to talk about size. Magnesium is just a little bit smaller. And so as a result, it's going to require a little bit more energy to take away the valence electron. So if we look at the first electron, which is in this first group here, if we look at the first one and we compare these two together, well, it increases as we expect because now it's 738. So it has 2 valence electrons. So the second electron is the second valence electron. So the energy just doubles. All right, it takes twice as much energy. Now, when you try to remove the third electron, now you move into that different type of electron. So now we're into our core electron. Big difference. So you have valence and core. Look at the difference in the energy it takes to remove a core electron versus the valence electron. So that's how you know that you're getting into the core electrons. It's an obvious change. And if you notice, this pattern continues on. Now, aluminum has a little bit smaller. It has 3 valence electrons. So you have 1, 2, 3, and then the fourth one represents the core electron. All right, so now I could keep going with this pattern all the way down the chart, but what I do want you to see is this, okay? So there should be a consistent pattern. As you go left to right, the ionization energy should increase for the first ionization energy. So we're looking at I1 only right now. So 495 to 738, that increases. 738 to 578, that decreases. So we're going to mark that for a second. Then we go from 578 to 786 to 1012 down to 1000. So notice the change is going up, but then it goes back down. And then it goes back up, and then it goes back up. All right? So there's a fairly consistent pattern with it increasing. There's just two places where it doesn't follow the pattern. Now, if we go and we look at I2, let's look for the same type of pattern. So it goes up, then it goes down, then it goes up, 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 and up. So everything's fairly consistent. Then we go here, we're going to look at I3 now. It goes up, then down, up, up, and up. I'm going to keep doing this. Up, down, up, and up, down, back up, and then up, down, and then this is just up. So now if you notice something here, if you notice, look at where this is showing you here. You see a very distinct pattern show up within the ionization energies in each of these successive losses of an electron. Now you do see it here, but this doesn't show up anymore. So this only happens here at this point in time. So let's talk about what's happening at this point here, okay? So this goes back to your electron configuration specifically. So we're only going to focus on the electrons found in the 3s and 3p shell, okay? So we're not worried about any other electrons. So just your 3s and your 3p. So if we look at magnesium and we look at aluminum, all right, and I find, so you have your 3s and your 3p, and you have 3s and 3p. Remember that this is just electron configurations. There are 3 orbitals in your p shell. There's 1 orbital in your s shell. Okay, that's not going to change. We talked about that in quantum mechanics. Now for magnesium, there are 2 valence electrons. So you have 1, 2. For aluminum, there's 1, 2, 3 valence electrons. Now if you pay attention here, you see that there's an oddball. And I say this for reason. So there's an oddball. The oddball is this 1 electron in aluminum. How stable do you think that 1 electron is in aluminum? Do you think it's very stable? Yes or no? Anybody want to answer?
No.
Right, it's not. So really what happens here is that this aluminum, even though it has 3 electrons, this electron gets kicked out very quickly. And so that's why the energy for aluminum is smaller than the energy for magnesium. It's because of the configuration that's taking place. Now, you see this pattern show up consistently all the way through I6. It is the same reasoning, because as you lose these electrons, they adopt this type of configuration in every one of these examples here. It has the same configuration, and this 1 electron by itself is so much more unstable because it's by itself. The element is ready to just get rid of it on it, very easily and quickly. So that's why you see this pattern. We call this an anomaly. All right, you'll see that word show up in the PowerPoint. We call this an anomaly because it's not something that we expect, but it's something that we observe, and this observation is because of this electron configuration that shows up. This pattern explains why we see this show up here. Does everyone understand that pattern? and that this one electron is going to get kicked out very quickly because it's unstable. Okay, so I'm going to go through some of the slides here. Now, we talked about going left to right. So we talked about the pattern going left to right, but the other pattern is from bottom to top. So you can see there's an increase in the size as you go from the bottom of the periodic table to the top, and that's because of the size of the element. As you go higher up, the elements become smaller, and the smaller the element, the higher the ionization energy. Just a very simple pattern. So if we were to draw two arrows here based off what we talked about last time. All right, the first arrow that we drew was this direction. This dealt with atomic radius, where it's increasing in that direction. All right, so that was the directional change for the pattern with atomic radius. Now in this topic with ionization energy, it's the opposite. So the ionization energy is increasing in that direction. Okay, so it's the opposite direction. All right, so as the atoms become smaller, the ionization increases. That's just a typical pattern, but keep in mind that we did talk about this weird thing that takes place with the electron configuration. All right, so moving forward here, now let's see here. So generally, as one goes across the row, it gets harder to remove an electron. As you go from left to right, the effective charge increases. However, there are two apparent discontinuities in this trend. The first occurs when group, we just talked about this here. So you see this showing up here again. It shows up in every one of the periods that we come across, and then you see that second change that shows up here, but that occurs just in that first group, and then if you get through that first group, it starts to back off a little bit. So all has to do with the electron configuration. Let me get a different color here. I can't stand that green. Let's see here. All has to do with the electron configuration. All right. Are there any questions on that? You guys are being so quiet today. Okay. So again, electron movement comes from doubly occupied orbital. Repulsion from the other electron in the orbital aids in this removal. So we're talking about the second one here. So this is the second one. So I'm going to show you how this one looks. This is the difference between phosphorus and sulfur. All right. So phosphorus has 5 valence electrons. Sulfur has 6. All right. This is in group 3, or period 3, I should say. So again, you have 1, 2, 3, 4, 5 for phosphorus, and then you look at sulfur. It's got 1, 2, 3, 4, 5, 6, and so again, you see this oddball right here. So this orbital has 2, whereas if you look at the phosphorus, there's only single electrons. Remember that electrons repel each other. So these electrons being by themselves in the orbitals are perfect for phosphorus, but when you look at sulfur, you have this one extra oddball here. So this electron here is going to get kicked out. It's going to be moved on to somewhere else. very quickly. So that's why it's lesser energy to remove it compared to the phosphorus. Phosphorus is more stable than sulfur for that reason. And that's the explanation for the rest of these eyeballs that you see here, these anomalies that show up. So since you guys aren't really asking questions, I'm gonna go on then. So electron affinity is the energy change accompanying the addition of an electron to a gaseous atom. So I'll give you a second, write this down, and then we'll move on. All right, so this kind of goes back to the point of atomic radius. So as you go from left to right, we know that the size gets smaller. And when an electron absorbs into an atom, sometimes the atom gives off energy. And this is really represented by the electron affinity. So what's the affinity of an atom towards the electron that's being absorbed? Some elements are like, well, whatever. Some elements get really excited. And so elements that get really excited give off a lot of energy. They release energy. Some elements that are not so excited, they don't give off much energy at all. So when you talk about the difference between group 1A and group 7A, there's a big difference between those two groups. Group 1A, much larger elements than 7A, first of all. Secondly is they don't have but one valence electron. So if they absorb an electron into their outside electron cloud, they're like, whatever. They give off a little bit of energy, not much. But group 7A, they absolutely love electrons. They have a high affinity for electrons. And so when there's extra electrons coming into it, they get excited because now they're happy and they release a lot of energy. So there's a pattern that shows up here. So as we look at lithium and we look at fluorine, just a quick example here, lithium releases about 60 kilojoules per mole of energy. So it's negative because it releases it. Now the pattern's not perfect, consistent across, but you get the point as you go left to right, it does increase. Now if you look at fluorine compared to that of lithium, fluorine has much more energy released than lithium because fluorine is a smaller element and it has a high affinity for the electron. So the higher the affinity, the more energy that's going to be released. That's what you need to learn from this particular slide. Any questions on that? All right, I need a volunteer. I'm just going to use Cassandra because she was helping Kay. Now, Cassandra, can you turn your mic on and let me know if someone has a question in the chat box because I can't see the chat box.
Okay, I will.
All right, has there anybody asked any questions or people been fairly quiet?
They're quiet today.
I see that. Yeah. All right. Well, thank you. Okay. Moving right along here. All right, and I'm not going to get into any discontinuities in this trend. I'm not going to worry about it. All I care about you understanding is that the smaller elements get the higher energy that's going to be released because they have higher affinity for electrons. All right, so that's what I want you to get from this. So moving right along here, boom, we're done with that. So now periodic table is found right here. So what I want to do is just talk about a couple of the characteristics that you see. So remember that as you go up and to the right, the ionization increases in that direction. And the electron affinity as well, just keeping it simple here, all right? So as you go from bottom to left, or top to bottom and left, your atomic radius, and I'm just going to abbreviate that, AR, increases. All right, so those are the three patterns that we talked about. All right, and if you have questions, feel free to ask. Cassandra will let me know. So now the next thing I want to do is look at this pattern here, and I want you to see metallic character. So metallic is, metal. All right, so first of all, we have to understand that the black staircase that you see where the purple elements are, that separates the metals from the non-metals. The non-metals are actually on the right, metals are on the left, and the more farther to the left you get, the more metallic you get. So the element that's most metallic is down here on the bottom left-hand side. And so that's the characteristics you need to be able to see here, is that over and down, you are increasing in your metallic character, all right? And that's because of the location of it on the periodic table. The further up and to the right, the more non-metallic you're going to be, and that just makes sense because your non-metals are found over here, and your metals are found on the left-hand side. So it's just a simple common sense thing. Now, the next pattern I want us to talk about are melting points and boiling points. So these are actually going to be, they're together. So as you go in towards the center here, I'm going to draw two arrows. As you go in towards the center, you're increasing in the melting point and the boiling point. So these elements right here have the highest melting point / boiling points. Okay, so that's not something that you're going to see, stated explicitly in this PowerPoint. It's something that I'm telling you explicitly. Okay, so you need to remember that. You need to write notes of that. So now, one thing I can say also is this. This is actually a really interesting fact, and the observations it's actually really fun to see it. So metals typically, when you think about metal, people think about iron, and you think about take a hammer and hit it on a piece of iron. It goes clink, 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 clink. I'm hitting a hammer on a piece of metal, by the way. So metals that are found in the very middle are very hard. All right, they're very hard, and they're not malleable. Malleable just is a way of conforming. You can hit the metal and bend it into shape. So the harder the metal, the less malleable it is. Okay, so high melting points, high boiling points typically result in very hard metals. Now, as you go towards the left on the periodic, you're going to have to write this down, okay? As you go towards the left on the periodic table, the elements start to become really soft. In fact, the group 1 metals are so soft that you can take a butter knife and you cut straight through it. It's just like cutting through butter. So on the left side, you're really soft. As you go towards the center where iron is, you become really hard. Now, the further to the right you go, and we're talking about as we start to get over towards this right-hand side. Now, lead is an exception to this rule, but normally when you get to these elements that you find in here, they become very brittle. And brittle means that if I hit it with a hammer, it shatters into pieces. So bismuth is a metal, last heavy, stable metal on a periodic table, but it's very brittle. And if you drop it or if you hit it with a hammer, it shatters into thousands of pieces. It's like taking a piece of ice and hitting it. It just goes everywhere. That's what we talk about as being brittle. Whereas iron, if you hit it with a hammer, the hammer is going to come back at you because it's very hard. It doesn't bend very much. So malleable, again, is just how the metal is able to conform whenever you hit it with a hammer. All right, so and towards the center, very hard metal object. Towards the left, very soft. And towards the right, they're very brittle. Just common characteristics, physical properties of those metals. Now, this table here that you see where it describes metals versus non-metals, I think that you should either take a picture or you should write it down because you need to remember the characteristics between the two. So these are the important properties to make note of. Metals have high luster. You can tell a metal from a non-metal. If I hold a piece of aluminum out, you can tell it's a metal because you see it's shiny. If I hold out oxygen gas, it's just oxygen gas. You see it all around. You can't really see it. There's nothing there. Some of them have colors, some of them don't. All right, the solids are brittle. All right, silicon is very brittle. And your computer boards, if you hit it with a hammer, it's going to shatter into pieces. All right, poor conductors of heat and electricity. That's why we use silicon, because it does not heat up and conduct electricity. But we do use copper and gold because they are excellent conductors of heat and electricity. Don't stick a fork in the outlet. You know why? Go put it in, you'll find out why. Don't do it, really. I want to see you guys in lab. And then, all right, so metal oxides are ionic solids. Most non-metal oxides form acidic solutions. So this is an important property here. All right, so that's something to make a note of. And we already know that metals form positive ions and non-metals form negative ions. So again, this is an important table. I would write it down after we're out of lecture here. It's too much to write down at this point in time. But take a picture of it, make sure you write it down, and make sure you learn the small differences between metals and non-metals. So you see the chart here that talks about metals and the different charges that the metals can adopt, and they all are positive, so they're cations. Non-metals will form anions, which are negatively charged. The noble gases don't form charges. Metals, lustrous, malleable, ductile, good conductors of heat and electricity. Compounds formed between metal and non-metallic tend to be ionic. We talked about that very early in the semester. Metal oxides tend to be basic. Non-metals, dull, brittle substances, poor conductors of heat and electricity. That's why if you ever buy a house and you look at the glass windows that it has, you want a double pane window. The double pane window in the middle of it has a gas that does not allow heat to pass across it, so it actually is an energy saver for your house. So substances containing nonmetals are molecular compounds. Most nonmetal oxides are acidic. And that goes, I'm just going to give you a simple reaction here. So SO2 reacting with H2O will form H2SO3, and that could go on to form H2SO4. H2SO4 is sulfuric acid, and sulfuric acid is a strong acid. If you are ever near volcanoes, volcanoes have a very smelly gas that comes out. It's sulfur gas, and sulfur gas reacts with the water near the volcanoes, and it causes that water to become very acidic, and sulfuric acid is the acid is forming and because of it. So just a quick example there. Then we get the metalloids. Metalloids are a combination of metals and nonmetals as far as their properties and characteristics are concerned. So it's a mixture of the two. You can't really say this one has this or this one has that one. It just depends on the metalloid. All right, so a good example is silicon. Silicon actually looks like what the picture's showing here. It looks like a metal, but it's brittle and it has poor conduction of electricity and heat. So metalloids are a combination. They're like a freak of nature. In other words, you can't just say that it's a metal or it's a non-metal. It's a metalloid. That's why there's that staircase there in the middle of the periodic table. And so that really gets us to the end of our PowerPoint. And there's a few other slides here, but this just shows you the butter knife example I talked about earlier with this is sodium metal. And sodium metal, you can cut it with a metal knife. It's very soft. But the only difference is if you take sodium and you get it in contact with the moisture in the air, it's very explosive. It blows up. So